Out the history, motivation, and progress of non-CDM dark matter science.
Yeah, thank you very much. First of all, let me thank the ITC, the organizers, and I in particular for the invitation and for having such a nice conference and for the opportunity to speak here and talk about something interesting about dark matter. I was kind of jealous looking at nice pictures like this yesterday and earlier today. Um, this is, by the way, the JWST image. And I thought, well, I should probably start my talk with something like this. And here's a photograph of dark matter universe. Probably it's not very instructive, but anyway, that's what we have. So I thought, well, if it's not instructive, maybe I should go and present some data from the experiments. And that's what I've got. The object not found. So without any success having anything specific here, I am going to do some theoretical presentation with a certain base in observational astronomy. So without further ado, let me go forward. And first, I'm gonna just start the discussion with history and motivation. I tried to find the moment when dark matter, alternative dark matter models, alternative to CDM, actually appeared. Before we had hot dark matter, warm dark matter, and cold dark matter 1, large-scale structure formation, it works real well. But at some point, people started thinking about something else, some modifications to dark matter because it works on large scales. The CDM works on large scales, but not so well on the small scales. So the paper, one of the papers I found is from 1994, evidence against dissipation-less dark matter from the observation of galaxy helix. And in particular, it says that the CDM is fundamentally inconsistent with recent observations. Remember, it's 1994. We're still debating whether we have inconsistencies or not, but that's what we have. Another problem, and by the way, the previous one, of course, you've read that. This is the core cusp problem, whether the inner parts of the galaxies actually have the Navarro-Frank-White type profile, which is cuspy, or more mildly cuspy or non-cuspy chord profiles where density is not blowing up. The next one is the substructure problem. And again, that appears and probably even disappeared by now. But the first paper on the substructure problem was 1993. And further, it's been elaborated by a paper in 1999. Both of them basically say the same thing, that the number of satellites, regardless of how you measure them, is inconsistent with simulations. And simulations predict way more. When I was actually working on this slide, I actually noticed an interesting coincidence. I don't know if it has something to do, probably it has nothing to do with me, but 1993 is the year when I came to the United States. In 1998 is when I came to Harvard. I'm hesitant making any specific comments here or taking responsibility for alternative dark matter, especially because I'm working in particular on some aspects of it. But there is an interesting coincidence anyway. Finally, there is a too big to fail problem. Basically, it's still the satellite problem. I at least view it as a satellite problem, although some people actually view it completely differently in terms of the star formation rate in small galaxies and dwarf galaxies. And the point here is that the fairly big satellites that we see in simulations and they're big enough so that the star formation is not going to be modified in them too much, those satellites are absent in the local group for some reason. And it's either our solar system, our local group, our Milky Way, is different in some ways than the majority of the galaxies, or, and that's actually in the abstract, or we need some different dark matter physics in here. Right. So there are actually more tensions than those at present. I just named 3 of them before, and now we have a satellite planes. Well, whether this is a dark matter problem or is it just structure formation problem that we don't resolve in computer simulations that well, it's hard to tell. The problem with the galactic bars, in particular the bar in the Milky Way, the bar pattern speed is larger if you have a non-chord profiles, and it seems to be inconsistent with observational data that we have from Gaia, for example. And softening the cores would actually help here. There is an ongoing argument whether we have the profile diversity in simulations, and we do have them in observations, certainly. Some galaxies show Cosby profiles. On the other hand, some others show well resolved chord profiles. Can you make a model that fits everything? Well, probably one can, and the model is not going to be that sophisticated, because when you add some interactions in the dark sector, collapse can occur, gravithermal collapse, and therefore mergers and collapse altogether will determine the fate. In other words, the merger will essentially reset the clock for the collapse, and therefore this galaxy will not be as evolved as the other one, and that explains the diversity. There is a problem with supermassive black holes. And again, it's not a big problem. One can make black holes by accretion, but they need to accrete pretty rapidly in the high redshift universe. On the other hand, it's possible to make supermassive black holes simply from the collapse of dark matter if dark matter is interacting, because dark matter density is very high in the early universe. So it's possible to make it there. And the final thing here is the WIMP miracle, and a lot of people actually throw stones at me for saying that, but I will still say the WIMP miracle is gone, and probably WIMPs are gone in their standard incarnation, because the cross-section, which is dictated by the WIMP mass, and the cross-section plus the expansion of the universe plus the mass of the WIMP again provides just enough dark matter so that omega matter is 0.3. Well, that's probably gone. One can tweak the model, and a lot of people actually do that, but in the simplest version, that's definitely gone. Models, that's the next thing. There are many models which actually try to introduce some modifications of dark matter in the dark sector. And I think the first one who actually opened the Pandora box is the self-interacting dark matter of Spergel and Steinhardt in 1999. This is a very good model, in fact, where they just postulated that there is elastic cross-section for dark matter particle interaction. And that helps them to resolve the Cosby profiles and make them more chord. Pretty quickly, within a year, there were 2 other models proposed. One was by us, simply the extension of the SIDM to flavor mixed particles. And that's a really minimal extension. We're not even producing any additional particles. We just say, well, they are flavor mixed like neutrinos. And that helps solve other problems as well. And there is a fuzzy dark matter model, which proposed that a dark matter is simply some unknown particle with very, very small mass, something like 10 minus 24 eV. And the whole idea here is that if you have such dark matter and it's non-relativistic, then the de Broglie wavelength of it is going to be on the order of a kiloparsec, and that's how we actually put the mass in, because we want to have that scale to be around the kiloparsec, and this helps us make cores in the centers because of simply quantum uncertainty. Then there is a number of other models, and they followed in the next years. There is ethers, and Mark Fogelsberger actually touched upon that in his talk yesterday. Annihilating dark matter, it was popular, but probably it's not as popular now because there are some constraints that it doesn't satisfy. There is still the warm dark matter model, probably not as the main one, but first of all, it's a test bed for various AI things, for example. And also, one can try to add something like warm dark matter to the cold dark matter to make it multi-component, and therefore one can resolve certain problems as well. So there are those kinds of thinking. There are other models as well. For example, atomic dark matter. You can just postulate that dark matter sector is as rich as ours, and one can make dark atoms, dark nuclei, dark electrons, dark whatever, dark anything, dark chemistry. Maybe it's there, but it's definitely not passing the Occam's razor. Although, of course, we should be careful. Nature sometimes doesn't pass the Occam's razor. We have so many chemical elements here. Who would predict them? Action-like dark matter, that's pretty much like fuzzy dark matter, and there are many which involve inelastic, exothermic, endothermic reactions of various kinds. The whole idea here is to either take energy or deliver energy and puff up the dark matter helix, for example. So they are, in essence, similar in many respects, especially if you want to simulate. So there is a great opportunity to study all of them, at least to some zeroth order level in computer simulations pretty straightforwardly. In principle, all those models can be subdivided into two. The preset or the early type models where a certain scale is just fixed by the theory in the very beginning, and therefore we have, for example, the initial power spectrum being modified. There is a suppression at a certain scale, for example, and then you see how structure forms, and of course, because of the suppression of a power spectrum, small structures don't form. These are WDM, ethers, fuzzy, and all that. There are also models which are, let's call them evolutionary. So there is some property of dark matter, for example, interactions, that is there all the time. And as dark universe evolves, large-scale structure forms. So you form clusters and galaxies and anything else. And this process starts to affect the coalescence, merger of halos or processes inside halos on the fly. So as there is large-scale structure formation, there is something else, there is some mechanism that modifies things on small scales. And these are self-interacting dark matter, 2-CDM that we proposed, the excited and the thermic and exothermic models, and so on. And I'm a part of the DREAMS project. Actually, Shai presented it yesterday as well. Our plan here is to understand, so to say, to our abilities, of course, the nature of dark matter by simulating galaxy formation and using AI here. So DREAMS stands for Dark Matter and Astrophysics with Machine Learning and Simulations. And now a little bit of our 2-CDM model. I actually presented it before at various conferences, so I will be very quick here. So we simply propose that a dark matter is a flavor mixed particle. By flavor mixing, I mean quantum flavor mixing. So it's like a neutrino, and what you see here is an example of that. Two mass eigenstates, and oscillations in between, shown in thin lines, are actually oscillations. If it's a neutrino, it's going to be neutrino oscillations, but oscillations are possible in dark matter as well. Although this is not the main thing. Oscillations, oscillations should look like this. Two mass states propagate away, and when they overlap, when the wave functions overlap, there is this oscillation between the flavors. So one flavor goes to another and back. In addition to this known effect, there is a so-called quantum of operation that we proposed some time ago. This is a physical effect, and it's actually applicable to any quantum flavor mixed system. A particle can escape a gravitational potential without any energy being added to it. That's a really strange thing, right? You have a particle that's trapped there, but it moves around and experiences only elastic scattering, so no energy is added to it. Nevertheless, part of the wave function continuously escapes from the potential, and the particle finds itself far, far away from the gravitational potential. So it's like a Münchhausen effect. We actually called it a Münchhausen effect when Baron von Münchhausen lifted himself and his horse out of the mud by pulling his own pigtail. And since it's a true story, I believe this is a true story of dark matter as well. All right, so a little bit of cosmology, how this is applicable to cosmology, right? If we have such a particle, such a dark matter particle, it can escape from a gravitational potential, but whether it escapes or not actually depends on how much energy or how much velocity this particle gets once it experiences these conversions. So if the velocity is large, compared to the escape velocity from the halo, they will escape from the halo, and halo will shrink in size, shrink in mass. Actually, not necessarily in size, but will shrink in mass, and will change the mass function of the halos. If, on the other hand, the halo is large, the mass is large, and the escape velocity is large, then particles experience those conversions, but they don't escape. Instead, they simply get a little bit hotter, so it will look like cold dark matter plus warm dark matter inside such clusters. On the other hand, the interaction between dark matter, and this is true for practically any self-interacting dark matter model, interactions allow heat to get transferred, and we know that in Navarro-Frank-White halos, the temperature, the maximum of the temperature is not inside a halo. It's somewhere in between the center and the outskirts. So when you allow particles to interact with each other, the heat will be transported inward inside a halo. And this is bad for the halo because it will become isothermal, and sooner or later it will experience collapse, isothermal collapse, to form an isothermal sphere. There is a question of timing here. It takes quite a while for the collapse to occur. So first you form a core instead of a cusp. But if you wait longer enough, then you make cusp profile is even cuspier. Instead of r to the minus 1, it may be anywhere up to the r to the minus 2. But again, like I said before, if you have certain interactions with other halos, one can reset the clock and collapse will not happen. So the results actually show that one can explain practically everything. I mean, the model is rich enough so that one can remove small satellites, or you can keep small satellites and remove large satellites and so on. So the model really works, so it's better now to do comparisons with observations. And there was this question yesterday whether the baryons follow dark matter. That's important for Lyman alpha forest, for example. No, they don't. Here is an example of dark matter density and baryon density from the same dark matter plus hydro simulations. And you can clearly see that dark matter effects are way stronger than um, than the baryons feel. I mean, exhibit. But nevertheless, the effect is there, and it can be probed. Here are some simulations showing n-body hydrodynamic n-body and hydrodynamic simulations. N-body is the first column, hydrodynamic is the second and the third, and what's shown in the second and the third is dark matter and the gas from those simulations. They're shown separately. And one can see that CDM is different from two-component dark matter, and some gas features are different, but the differences are small. So the best thing here is to actually go through the redshifts and measure Lyman alpha 4s through the redshifts, and that will help us discriminate between the models, because as you can see, for example, the green model gives suppression at high redshifts, but enhances at low redshifts. That's the model kind of starting early, with cross-section being 1 over velocity. So it's very important that small velocities. On the other hand, the blue model does just the opposite. It gives some enhancement at early times, but suppressions later. So one can discriminate that, and I think this is the best thing. If you can do that, that's what we need. And observations, I hope, will help us do that. So whether we have a paradigm shift here, I would like to have it, but looking at how long we are still debating about dark matter, maybe not the next decade, but I do hope at least sometime in the future, we will get there and we will understand dark matter properties better. Yeah, this is it. Thank you.
Thank you so much. Okay, we do have time for questions. Thank you. Okay, so maybe completely off, but yeah, I recently heard a proposal that the dark matter could be a particle within standard model, and it is kind of that we haven't discovered all of the neutrinos because they all have the same handedness. So there are like 3 neutrinos to be discovered. And as you were discussing this model where there is flavor mixing, so I was just wondering, could this be a part of the solution that is actually 2 right-handed neutrinos?
Excellent question. Actually, I thought about that myself too. The answer is, if those sterile neutrinos interact with themselves strong enough with large cross-section, then yes. But neutrinos in general, at least the neutrinos that we know, interact very weakly. So then it's not a solution, because you need flavor mixing and interactions between them. 2 things. The cross-section must be relatively large, actually very large, I should say. It's 1 barn per GeV.
Thank you.
Thank you very much. In the list of possible tensions that you put at the beginning, you put the core versus cusp and the profile diversity as 2 different possible tensions. But from my understanding, this is the same thing. Could you maybe clarify what is your reading of the observational literature about observational inference of core and cusps? Because, yeah.
Okay. I agree that in general this is the same thing, but this is like 2 sides of the same coin, to me at least. I mean, I'm not pretending being the last, giving you the last word here. But my understanding here is that suppose you resolve core cusp problem in the sense that you produce cores. If you always produce cores, then it's bad. So you need to explain how one can make cores in one type of systems, and keep cusps in others. So my point here is simply, we have to have a model which is rich enough to let you do that both. Right, but in general, I agree with you.
Unless the baryons do the job.
I'm sorry?
Unless the baryons do the job of diversifying.
One can play with the baryons as well, yes, but I'm thinking about this from the point of view of dark matter. If baryons do the job, I'm happy and I leave the room.
I was wondering what you think about primordial black holes as a dark matter candidate. You haven't mentioned that option.
Yeah, well, there is this paper, actually a series of papers, by Jerry Stryker and his student, that if you have dark matter interactions substantially large, then you can get rid of the momentum and angular momentum if it exists, and let this dark fluid essentially collapse into a black hole to form a black hole. So the idea here is to have enough interactions so that one can treat accretion as fluid accretion rather than collision-less accretion, because fluid accretion is way more efficient than collision-less. And then one can estimate how much mass this newly formed black hole should be, which is really relatively easy. You just estimate the time scale for the formation and compare and see what the region is occupied by dark matter of substantial density, so that the mean free path is small enough. And once you do this estimate, you get, you get the reasonable result, but the problem is that we don't know what the cross-section of dark matter is in terms of dependence on the velocity, and it gives you whole diversity of masses.
Hi. Thanks for your talk. I have a very short question. So fuzzy dark matter seems to be ruled out. There are many observations, at least in some range of masses. Do you think it's still interesting to explore with more high-resolution hydro simulations?
I'm glad that you've said that. I'm with you on this.
Okay, well, with that, thank you so much, Misha.
Thank
Thanks
you
so much to all of our speakers. We do have 5 minutes to take a very short break.